Hello, and thank you for joining today's presentation in the Richardson RFPD webinar series, A Walk Around the Block. In today's session, Michael Kuhl, an engineering manager at Unique Technical Services, provides insight into the engineering necessity to select or design a supercapacitor module that fits your unique application. So without further delay, let me turn it over to Michael Kuhl. Michael, go right ahead.
Hello, ladies and gentlemen. My name is Michael Kuhl. I have a background in mechanical engineering and have designed and integrated multiple ultracapacitor modules in a variety of applications over the past 10 years. Currently, I am the engineering manager at Unique Technical Services. UTS provides engineering services to a variety of clients. We have electrical, mechanical, software, and power electronics expertise. The UTS team has worked with ultracapacitors for over 10 years and has worked in the energy storage space for over 25. Today, we are going to talk about guidelines and best practices for the design of ultracapacitor modules. Ultracapacitors are an ideal storage solution for high power, low energy applications or for cyclical power cycles. The long life of capacitors compared to batteries, combined with the benefits of their low resistance and self-heating, make ultracapacitors the superior design choice in many cases. However, selecting a robust and reliable cell is only the first step. There is engineering effort necessary to match the solution with the application. That engineering effort can be often a barrier for a company to select ultracapacitors even when the application is right. UTS in this presentation will provide a how-to instruction on this engineering. This presentation will cover the steps necessary to correctly match the energy storage capacity target for the application with different ultracapacitor sizes, while keeping in mind the voltage and current limitations of the power electronics. Attendees will learn that cell capacity and series parallel configurations provide many options and variables to configure to achieve the best solution. This presentation will also address the typical means to achieve other features of ultracapacitor modules. Attendees will see mechanical features that address physical sizing, weight, vibration protection, and thermal management. And finally, UTS will cover common control requirements, namely cell balancing and module feedback communication methods. So let's get started. For the purposes of this presentation, we will assume you have a good handle on your needs and requirements. For instance, you know that your application requires energy storage in this voltage range, with this amount of current required for this duration. You know your size and space constraints. You know the ambient conditions of the environment. And you are ready to make decisions on the rest of the system, like what controls to put in place and what power electronics to use. As I said earlier, the best applications for ultracapacitors tend to, among other things, need high power or high currents, or repeat a cyclical charge and discharge profile. If we think about some example applications, maybe an ultracapacitor module acting as load leveling on battery storage, or perhaps a bank of modules act as bulk storage for a high power gantry that repeatedly accelerates and decelerates a large load. But in nearly all cases, the application requires more than one cell, and so those cells need to be configured in series and parallel strings to achieve the electrical requirements. So, knowing that you have fallen into the right category, namely that ultracapacitors are a good solution, the first thing that needs to be done is electrically sizing the module. So we look at the energy storage requirements, the voltage range and current limits or requirements. Specifically, how much power do you need in watts, and how much energy do you need to store in watt hours? First, let's talk about capacity. Ultracapacitors are rated in farads. The equation to calculate the capacity of capacitors in series can be reduced to the cell capacity over the number of cells, if all the cells are uniform, which they typically are in a module. For parallel strings, just sum the capacity of each series string. To convert to watt hours, you can put in the voltage range and the capacitance in this energy equation. It is advisable to use 80% of the nameplate capacity, as ultracapacitors' end of life is characterized by 80% of its capacity. Next, voltage. Capacitors in series will add their voltage, while capacitors in parallel must have the same voltage. You must remember that capacitors lose their voltage as they discharge, so the nameplate capacity of a string is only valid if you can discharge them down to 0 volts, which is uncommon with power electronics. Also, it is worth noting that running a capacitor up to the peak voltage will reduce its life expectancy, so if possible, it's a good idea to derate the peak voltage. And of course, it's important to match the power electronics usable voltage range to the ultracapacitor module voltage. As for the current, the power electronics may limit the amount of current you can pull from the storage, but typically you want to limit the current to manage losses. If we remember power is I squared R, then lowering the current is a major factor in reducing losses and therefore heat. Since capacitors have very low equivalent series resistance, or ESR, that R value is very low compared to other storage methods, like batteries, but it still needs to be managed. Keeping the cell temperature low is another important aspect of module design. For keeping the cell temperature below its peak allowable temperature will improve life expectancy, just like keeping the voltage below its peak allowed voltage. So let's use an example. Say I have a load leveling application where I would like to use a DC to DC converter to supplement a battery pack. The typical cycle is to discharge the capacitors at 10 kilowatts for 10 seconds and then slowly recharge at 10 amps. This procedure would repeat every 15 minutes. The DC to DC input range is 75 to 125 volts, and the DC to DC can peak at 200 amps. If we calculate the energy for that 10-second load and factor in some worst-case efficiency, we find we need about 35 watt-hours. With some back-of-the-napkin calculations using simple energy equations and the cell performance parameters we get from cell manufacturers, we can start to figure out what size module we need. First, we see that to use the full range of the DC to DC's input voltage, we need a module of 48 cells. Again, we use a cell voltage below the max allowable to maximize life expectancy based on the manufacturer's recommendations. Then we quickly calculate the total capacitance of a single series string. Next, we calculate the energy capacity of the 48 cell module using the achievable voltage range of the power electronics. Finding that the capacity of the single string is more than the needed 35 watt-hours from the previous step, we can proceed. Next, we check how long a 10 amp constant current charge would take to recharge the full capacitance. These equations are linear only because of constant current charging. If instead we used constant power charging, the equations would be more complex. But using the linear equations, we can see how long a constant current charge cycle would take. So now we can characterize the current profile that the module will experience across this whole cycle. Using that current profile, we can determine the average current, which we will use in the next step. Knowing the cell ESR from the cell manufacturer and the application's average current from the previous step, we can simply calculate the expected I squared R heating losses. We use twice the ESR value as the resistance can increase at the end of life of the cells. Finally, we check the temperature rise on the module. Here we have assumed a thermal resistance of 5 degrees C per watt. This value needs some engineering justification though. We'll talk about this later on. But here we can at least determine if it is acceptable or unacceptable to proceed. But as you can see, understanding and controlling the thermal resistance and electrical resistance of the module becomes very important. Now we come to the second phase of developing a module, physically configuring the module. Assuming now you know the number of series cells and the number of parallel strings necessary, you can determine the best module size. You may find a single module is acceptable, or that a parallel series configuration of modules is necessary. But either way, we can focus on the design of a single module now. We again start with the requirements: voltage isolation, mechanical vibration or shock protection, thermal management, and others. So, where do we begin? To think about the mechanical features of the module, the best place to start is to think about the cell construction, and therefore the cell's potential failure modes. Most ultracapacitor cells are made up of a jelly roll of a metal and dielectric rolled into a cylinder, and then stuffed into an aluminum can. There is typically an electrolyte solution in the can, and the terminals are at each end. In this type of construction, the can is crimped and sealed on one end. One terminal and the can are typically one voltage node, while the crimp isolates and seals the opposite terminals to the aluminum body. Understanding this construction leads us to understand the limitations or failure modes of the cell. The crimp feature is critical, as it seals in the electrolyte and isolates the one terminal from the can. If the crimp's seal fails, you could get leakage and lose capacity. Or if the crimp's isolation feature fails, you could short the cell. Protecting the isolated terminal and the crimp are important aspects of module design. The best way for me to think about it is imagining a disposable paper coffee cup. The lid holds in hot coffee and adds some rigidity to the cup, just as the crimped end of the can holds in the electrolyte and adds some rigidity to the capacitor. But if we start pulling or twisting on that lid, you would quickly come to expect that sooner or later there would be coffee all over the floor. Now, ultracapacitors are not so fragile as coffee cups, but a well-designed module can last 20 years, so it's worth understanding the potential problem areas. So now we know we have to protect the cell crimp. But first things first. First, we have to string up the cells in series. We do this by securing bus bars to the terminals and bridge positive to negative. With capacitors that have such low internal resistance, it is important that the connection be low resistance. We don't want the terminal connection to heat the cells. A bolted connection or a welded connection can both achieve very low levels of contact resistance and come with their own trade-offs. Welding can last longer, but is more difficult to produce and inspect, while a bolted connection is easier and can be disassembled. But it can, however, be more likely to loosen when exposed to thermal and vibrational cycles. So now if we look at the mechanical design needs, we find we need to protect the busbar connection and the cell crimp. In both cases, relative motion between cells can be the main problem. The connection can weaken to become a high resistance point, then a hotspot, and could eventually lead to cell failure. And the bus bars have now added a significant lever arm and a whole other body of mass tied to the crimped end terminal. This lever arm and added mass can make it easier to fatigue that crimp and seal. Again, let's return to the coffee cup analogy. The coffee cups are like the cells, and the cardboard is like the bus bars. And here it's like we're bridging one lid to another cup, and that cup's lid to another cup, and so on and so forth. We can see that lifting one cup in such an array is not a good idea. That relative motion puts all the lids at risk of popping off. So if we need to eliminate any relative motion between the cells, how do we do it? Well, we can do this with a variety of mechanical features. Perhaps we hold the cells in a structure, or even perhaps we bridge the bus bars with a non-conductive structure. But once the cells are secured relative to each other, the cell terminals and the cell crimp are well protected. So again, for a module, we start by taking any number of capacitors. We then apply bus bars to create our series and parallel configurations. We somehow hold the array rigidly together as a unit to avoid loading the terminal to bus bar contact, and of course the cell crimps too. But next we have to do three things. 1. Achieve a thermal path to ambient. 2. Achieve the necessary mechanical isolation from the housing. And 3. Achieve the required electrical isolation to chassis. Thankfully, achieving all three of these requirements is not impossible, even though they tend to be somewhat mutually exclusive. First, let's tackle isolating the array from any shock and vibration that could be transmitted into the housing. We often do this when packing delicate things to ship in a cardboard box. We intuitively wrap the items together in a tight bundle, then put foam or bubble wrap between the bundle and the exterior box. We can do this with ultracapacitors too. Some spring dampened material or feature between the cell array and the housing is advisable. Next, we look at the thermal path. it is helpful to revisit the cell structure again. Here we find that the cell as a whole is fairly well uniform, being mainly constructed from aluminum and filled with a liquid that avoids large air gaps. However, the paths of best electrical flow tend to be the paths of best thermal flow. So it may be helpful to consider the terminals, and therefore the bus bars, as not only a feature for electrical conduction, but also thermal conduction. And third, electrical isolation. Simply put, there can be no path throughout the life of the module that allows leakage current. It is important to consider the max voltage that the module could experience while considering the chassis as ground. You may design a module for 100 volts, but you could string 10 of them in series to gain 1,000 volts. Air can be an effective insulator, but only at low altitudes. However, this requirement usually drives an ingression protection rating just to avoid contaminants causing potential leakage paths, like dust and moisture. Some solutions for these three design challenges can be thermally charged potting. Potting can be effective for both thermal and vibration, but be warned, it can be heavy. Thermal pads. Pads can be effective thermal paths, but these require compression to achieve their nameplate characteristics. Rubber pads. If thermal is not an issue, simple vibration isolation pads can be very effective, especially if you can decrease the current through the module, thus reducing your I-squared losses. So now you know the size of your module, you know the electrical characteristics of your module, and you know the mechanical features you're going to include. So now we can talk about module controls and safety features. One good way to achieve a good electrical balance is to achieve a good thermal distribution. This underlines the importance of the thermal design we just discussed. But what do you do to mitigate the potential variations in cell capacity you're bound to experience from vendors? Well, you implement a balancing methodology. First, let's talk about passive balancing. Passive balancing is a circuit that removes charge from cells when triggered. Typically, the circuit monitors cell voltage and triggers a resistor at a certain voltage threshold to discharge the high cells and have all cells match their voltages. This can be effective if charging is regular and there are spots of idle time in your duty cycle. You will typically have to size the resistor values based on cell capacity, expected dwell time, and continuous charge current. So if you have a duty cycle of, say, 16 hours per day, that leaves 18 hours of deep correction balance time available. But remember, charging up to full and then having all resistors active is not useful balancing. Only when the high cells are resistor active and the low cells are resistor off is the passive balancing effective. Next, let's talk about active balancing. Active balancing is generally a circuit that moves charge from high cells to low cells. There are many topologies for active balancing circuits, but in general, instead of using a resistor to dissipate charge on a cell and therefore create heat, the extra charge is moved to a low cell. This is a more complex circuit, but can be effective if there is a concern for energy efficiency or heat dissipation, or if there are not sufficient dwell times to use passive balancing. In any case, most likely, you probably want monitoring or feedback of some kind. You may require individual cell voltage feedback, sub-module or module voltage feedback, or cell temperature feedback. These are typically used for a stop charge signal that will keep an imbalanced cell from being overcharged and damaged. This type of feedback typically requires a printed circuit board in the module with a connection to each electrical node and a number of temperature sensors. The level of feedback and balancing is typically dictated by the system size or by understanding that the higher the working voltage of the cell, the closer you can get to a dangerous level. So there you have it, the basics of designing your own ultracapacitor module. As inspiration, here are just a few examples of modules we have produced. Here we have an ultracapacitor module and DC to DC converter paired with an electric ground support equipment vehicle's battery pack for load leveling. And here we have a bulk energy storage for a hybrid traction system. This module was designed to be low profile to mount on the roof of vehicles or underneath directly to the chassis. The thermal path on this module went directly to the case for convection cooling. And here we have a 120 volt module with an internal fuse and contactor. This module can be racked up to 1000 volts. So as you can see, we have designed multiple row arrays, single row arrays. We've used bolted bus bars and laser welded bus bars. We've used silicone potting and urethane pottings, as well as thermal pads. We've created modules with active cooling and passive cooling. We have created modules with passive balancing, temperature sensing, and even CAN communication feedback. Hopefully, you have gained some experience and know-how on some of the features you can include in your ultracapacitor module. If you still want more, you can contact UTS for assistance in finding a solution. Thank you very much.
Thank you to Michael Kuhl for today's presentation, and thank you from both UTS and Richardson RFPD for attending today's session. We look forward to you joining our other sessions in this series. Thank you all so much for being here today. Take care, and we will speak with you soon.